Hello everybody. So today we'll be taking a look at work, power, and also energy. So when you're doing any physical actions, such as pushing or pulling on an object, you're transferring energy from your body to the object that you're exerting that force on. This transferal of energy is referred to as work. Work is defined as the product of the force exerted on an object and the distance of the object, the distance that the object moves in the direction of the force. However, keep in mind that work is a scalar quantity, meaning that it has no direction. So the equation of work can be written as work is equal to force times distance, where W is work, and that is measured in joules. F is the force, that is measured in newtons. And D is distance, and that's measured in meters. And an important idea to remember for this is that work is only done if the object is moved in the same direction of the force that is being exerted on it. So let's say, for example, you're holding up a box, and you're keeping that box at the same height and walking forward with it. There would be no work done on the box because the force you're exerting is upwards to keep the box at that same level, and you're moving in a forward direction. So if we were to draw that out, you can imagine it like this. You're holding up a box, so you're exerting a force upwards on the box, preventing it from falling down. But then you're moving forward, which is in this direction. You see these two, the force exerted and the motion of the object, since they're in two different planes, one is vertical and one is horizontal, there would actually be no work done on the box. So let's just quickly do some practice problems with the idea of work. For question 1, a student lifts a 0.8 kilogram box at a height of 1.2 meters. How much work is done? Give you some time to work on that. So first, since we do not have the force, but we do have the mass, we can use the force equals mass times acceleration equation to calculate how much the weight of the box is in newtons. So the mass is 0.8 kilograms. That'll be times 9.8 meters per second squared, which is the acceleration of gravity, meaning that the force is equal to 7.84 newtons. And now using the work formula, since we have the force now and we also have the distance that the box was lifted, we can then find the total work done. Work is equal to force times distance. The force is 7.84 newtons times a distance of 1.2 meters. Therefore, the work done is 9.4 joules. Now let's do question 2. How much work is done when there is 750 newtons required to push a car 25 meters down the road? Take some time to do that. This is a much easier one. Write out your work equation. Work is equal to force times distance. You have the force. There's 750 newtons required to push it. Therefore, it is 750 newtons multiplied by a distance of 24 meters, which would make the total work done equal to 18,000 joules. Now, let's move on to something a little bit more complicated. Force and displacement at an angle. So in certain examples, the force applied to an object may be at an angle, such as when you are using a lawnmower. For those questions, you will need to use this slightly modified equation. So before we had work is equal to force times distance. In this case, we'll be using work is equal to force cosine theta multiplied by the distance, which you can also write out as force times distance cosine theta. So to help you better understand, I'm just going to draw out a triangle here. There we go. And now let's use this triangle for the first question. Number 1. All right, so a man is pulling a box and exerting a force of 250 newtons, a distance of 3 meters, using the rope. The angle at which he pulls is 50 degrees to the horizontal, with the horizontal. How much work is done? So for this question, first what I want you to do is draw out a triangle, which I've already done here. This will help you visualize the direction of the forces. So he's exerting a force of 250 newtons, and he's pulling it on the box, and he's pulling it a distance of 3 meters using the rope. The angle at which he pulls is 50 degrees, just right over there, with the horizontal. How much work is done? So what you want to do now is, using cosine, since you have the hypotenuse of the triangle, you can find the newtons of force exerted horizontally, which is the one that you want, since that is in the same direction as the distance that is moving. So we can just set this as x or something like that, doesn't really matter. And if it helps, I'll just draw the box here. You can imagine the hypotenuse is the rope that is pulling the box. So to find x, all we'd have to do, x is equal to 250 cosine 50 degrees. Therefore, x is equal to, if you pop that into your calculator, it will be equal to 160.7 newtons. So that'll be 160.7 newtons of force horizontally. Now that you have that, you can calculate the work done now. So you have the force and the distance. Force is equal to 160.7 newtons multiplied by a distance of 3 meters, which is equal to, and that'll be a total amount of work done being 482 joules. And that is the amount of work that is being done on the box while it is being pulled by a rope at an angle. So yeah, questions with angles, not that much harder. All you need to do is just know how to use cosine. So now that we have finished work, we're going to be looking at the idea of power. So when you were looking at the work equation, you can see that time is not factored in, meaning that push and create for 2 seconds or for 3 hours will all result in the same amount of work being done. Now this might be a little bit hard to conceptualize at first because, well, if you push it for 2 seconds, you're going to be less tired than if you're pushing it for 3 hours. However, work doesn't change, but power does. Now, power is the rate at which work is being done. And the equation for that is P is equal to W over T, where P is the power, and that is measured in watts, which is just written as a capital W. Remember not to get that mixed up with work. W is work, and that is once again measured in joules. And also T, obviously, is time, and that's measured in seconds. And that's measured in seconds. So pretty simple stuff. Now let's move on to some questions. Once again, these equations aren't really that hard to remember. There we go, number 1. A person lifts a 3-kilogram backpack, a height of 1.4 meters, straight up. They do this in 0.8 seconds. How much power is used in this action? You can rewind back, hear the question again, or you can start doing it now. I'll give you some time for that. So just like how we did before, we currently do not have the force. However, we do have the mass, and we know the acceleration of gravity, so we can calculate the weight of the backpack in newtons. So that'll be a 3.0 kilogram backpack times the acceleration of 9.8 meters per second squared. So the weight of the backpack in newtons would then be equal to 3 times 9.8, which is 29.4 newtons. Now that we have that, we can calculate the amount of work being done. Work is equal to force times distance. We have the force, 29.4 newtons, which is multiplied by a distance of 1.4 meters. Backpack's being pulled straight up. 1.4, so you'd have 41.16, and that's work in joules. Now that we have the work, we also have the time, we can finally calculate the power which was used in this action. So that'll be a work over time. That'll be a work of 41.16 joules over a time of 0.8 seconds. So that'll be equal to 51.45. That'll be watts, which would be rounded to, this is 0.80, which would be rounded to just 51 watts. All right, question number 2. A large bag is being pulled at 67 degrees using a force of 153 newtons. The total distance it needs to be pulled is 2.6 meters, and it takes 3 seconds. How much power is used? Once again, take some time to work on this equation. If you want, you can rewind and listen to it again. So since this question deals with an angle, we're going to need to draw a triangle first and also use a separate equation for work. So let's see, is pulled using a force of 153 newtons, so that'll be the hypotenuse, and that is at an angle of 67 degrees. It needs to be pulled 2.6 meters, and it takes 3 seconds. So what you want to do, first find x, the adjacent side, make sure that everything's in the same direction. X is equal to 67, x is equal to 153 times the cosine of 67 degrees, which is equal to 59.78. So we'll just write that as 60 newtons. That's the amount of force that is being applied to the large bag horizontally. The total distance that it needs to be pulled is 2.6 meters. So then we can use the work equals force times distance equation. Work is equal to 60 newtons multiplied by a distance of 2.6 meters. Therefore, work is equal to 60 times 156 joules. And then finally, now that we have all this information calculated, we can use that to find the power. So that'll be work over time. Work is 156 joules over a time of 3.0 seconds, which will then be equal to 52 watts. So that's the amount of power which is being used in this interaction. All right. Not that hard, just some simple equations, nothing to be too worried about. So now we'll be moving on to energy. So moving objects all contain a form of energy called kinetic energy. However, before an object has kinetic energy, potential energy is stored in this object, and then work is done to transfer this one form of energy to the other. Now, to better understand, let's think about the movement of a roller coaster. As the roller coaster moves up on the hill, so I'll just draw it out right here. As the roller coaster moves up on the hill, it is gaining potential energy and also losing kinetic energy. And at the very top of this hill, the roller coaster, this is where it has the max potential energy and also the least amount of kinetic energy. So we'll just write potential energy as EP. So right now at the very top, 100% of the energy is stored as EP, which is potential energy. And as it is falling back down, this energy is once again being transferred from one form to another. And this time, instead of while it was going up, it's going down now, so the potential energy is now being transferred into kinetic energy. So now halfway through the descent, 50% of the energy will be kinetic, and the other 50% of the energy will be potential. And as it is farthest down the hill, once it has gained the most speed that it can, it will have 100% kinetic energy and no potential energy anymore. Now the equation for kinetic energy is equal to, now you can write this as E, K, or you could also write it as KE, doesn't really matter. Just depends on how you like to write it out. So the equation for kinetic energy is equal to 1/2 mv squared. Give me just 1 second. Where m is measured in kilograms and is the mass. It's mass measured in kilograms. And v is obviously velocity. Velocity, and that's measured in meters per second. And also the energy is measured in joules, just like work. EK is the kinetic energy measured in joules. All right, so when you're dealing with kinetic energy, the change in kinetic energy is also equal to the total or the net work that is being done. So since these two are both measured in joules, you can actually sometimes use them interchangeably, although it depends on the situation and also the question. So the second equation will look like this. The work being done is equal to the final kinetic energy, which is EKF, minus the initial kinetic energy, which is EKI, or you can write it as EK naught. Now that we have this in mind, let's do some practice questions for kinetic energy, and then we'll move on to potential energy. So, a 0.500 kilogram ball is at rest and is kicked, and it has a final velocity of 15 meters per second. Now, how much work was done on the ball to give it the kinetic energy? How much work would be done if the ball had an initial velocity of 2 meters per second with the same final velocity? So let us calculate the two separate kinetic energies. So now, since the ball is initially at rest, we know that the initial kinetic energy would then be equal to 0 because it doesn't matter what the mass is. If the velocity is 0, that'll just be 0 squared multiplied by, and anything multiplied by 0 will be equal to 0, so that'll be 0 joules. Or sorry, 0.0. It's best to write it like that. Now moving on to the final kinetic energy. in the question it states that the final velocity is 15 meters per second. So we have the mass and we have the velocity, then we can calculate the final kinetic energy. Mass stays the same throughout because it's the same object, so we just use 0.500 kilograms. And that'll be multiplied by 15 meters per second squared, which is equal to 1/2 times 0.5 times 15 squared, that is equal to 56.25, and that'll be joules. So then, all you have to do to find the work is just put both of these kinetic energies back into the equation. Since it's final minus initial, you have 56.25 joules minus 0.0 joules. And then it is just equal to 56.25 joules, which is equal to 57. Or sorry, 56, I mean. You don't have to round it up. Which is then just equal to 56 joules. All right, now let's move on to potential energy. So potential energy, you can write that as PE or EP, doesn't really matter, once again, is written as EP is equal to mgh, where m is the mass in kilograms, once again. G is the acceleration of gravity. And that's in meters per second squared, or more specifically, it'd be 9.8 meters per second squared. And then h is the height at which the object has moved. Now, this height could be ground level, or it could be any point that you set as the reference point. So, let's say you're holding a backpack at a level of like 1 meter, and that's your reference point. Now, if you were to move it up to 1.5 meters, the increase in height would then be 0.5 meters. So then that would be the height that you use. It all just depends on the reference point, but as long as you keep the reference point the same, it doesn't really matter where you set it. So yeah, pretty simple stuff. Let's go on to a practice question for this. A ball with a mass of 0.750 kilograms is originally held at a height of 1.2 meters. It is then raised 0.5 meters straight up. What is the change in potential energy of the ball? Give you some time to do that. All right, so the equation that we'd have to use is what I just mentioned. EP is equal to mgh. We have the mass of the ball, which is 0.750 kilograms, multiplied by the acceleration of gravity, 9.8 meters per second squared. And that is held at a height of 1.2 meters. Once we multiply everything out, that will equal to 8.82 joules. That'll be the potential energy. Well, we can just write that as potential energy 1, since we're going to have to calculate 2 for this question. Potential energy 2, mg, and sorry, this will be height 1, and this will be height 2, is equal to 0.50 kilograms multiplied by 9.8 meters per second squared. And the new height, it is raised by 0.5 meters, so that'd be 1.2 meters plus 0.5 meters. Now, once you multiply everything out, that'd be 0.75 multiplied by 9.8 multiplied by 1.7. That'll equal to 12.495 joules, and that is the second potential energy. But what you want to do is, the question is asking you to calculate the change. And to do that, all you need to do is just subtract one from the other. So as you know, the symbol for change in is delta, which is just a little triangle. So that'll be the second potential energy, or sorry, the first potential energy subtracted from the second potential energy. So that'll just be 12.495 joules minus 8.82 joules, which is equal to 3.675 joules, and that is the change in potential energy from one position to another as it is moving higher. Now, when you're dealing with questions that involve both potential energy and kinetic energy in one object, there's an important idea that you need to understand, is that energy is never lost, right? And it is only transferred to a different form. And this is called the law of conservation of energy. So let's go back to the roller coaster example. So in the roller coaster, there is always the same amount of energy present. However, as it is moved up, this total energy is just being transferred to a different form. So at the top of the roller coaster, let's just say, for example, just for the sake of some easier explanation, let's just say that this roller coaster has 100 joules of energy. All right. Let's just say that it has 100 joules. Now, at the top of the peak, at the top of the hill, this is where it's at its maximum height and where it's at its lowest speed, because for that one moment, it is completely stopped. It's completely stationary. So that means that there is zero kinetic energy in this roller coaster, and 100% of the energy, 100% of the rest of the energy is potential energy. So that means that there'll be 100 joules of potential energy. Once it's moved down, there will now be, since it's halfway through its descent, it is halfway to its highest speed. That means that 50% of the energy will be kinetic. So out of the total 100 joules of energy, 50 will be kinetic, and then 50 will be potential. And finally, once it reaches the bottom, that's where it'll be at its lowest height, but also its max speed, meaning that there is 100% kinetic energy. So once again, it has a total energy of 100 joules. However, all 100 of those joules are kinetic energy. So that's basically just the law of conservation of energy. So the equation for this is then equal to E, which is the total energy, is equal to the kinetic energy plus the potential energy, where they're all written, or sorry, they're all using units of joules. So now finally, for question 3, using the information from question 2, find the maximum kinetic energy of the ball if it is dropped. I'll give you a second to do that. Shouldn't take too long. So now that you know that, now that you know about the law of conservation of energy, you'll know that potential energy, or sorry, the total energy in an object will never change. And since you already calculated the maximum potential energy that the object has, then we'd also know that what the maximum kinetic energy the ball would have once it is dropped. So if we just look at what we wrote before right here, this is the maximum potential energy that the ball can have, 12.495 joules. So if we imagine the ball being held up here, this is where 100% of its energy is potential, and that is 495 joules. If it is dropped, once it reaches the very bottom, all of its energy will then be transferred to kinetic energy. Therefore, the maximum kinetic energy would just be 12.495. And there we go. So that's about it. That is power, work, and energy done. It's not that difficult, just some simple equations. All you need to do is just remember all of those, and you should be fine.